Uh, Hello, this is module 8, and it's about network layer. So far, we're covering these chapters in layers. In layers. So far, we have covered physical, data link layer. Now it's network spot, which will be, I think, chapter 14. Yes. Of applications. Then session, presentation, and then action. Yes. So that is the hierarchy or the order. The areas within this, the areas that you're going to go through the topics. We have network layer, characteristics, then IPv4 package, IPv6 packet, how a host routes, and then router routing table. So network layer characteristics. The network, it provides services provide services to allow the edge devices, all what we call the end devices, to exchange data. So IPv4 and IPv6 are principal network layer communication process. In other words, there's a principal, meaning that minus IPv6, then there is no any other protocol that is going to help the end-to-end to communicate. They can actually have other protocols. They can actually miss other protocols, but this they should the IP either V4 or A6 it should not miss. So these other protocols, it's a must they have to use this protocol, IP Internet Protocol. So the network layer performs four basic operations where we have addressing end device. So the end device, they have to be assigned with IP address, then encapsulation. So the network layer, what it does, once it receives a frame, it checks that frame. Once it receives a, a package, then once it receives a frame, the frame, it has to be checked. It has to be checked. The source MAC address, then destination MAC address. So once determining the destination, the packet destination, then the layer 3 device, it can encapsulate. So at the time when the layer 3 device decides to send, then it means that it has to first encapsulate that package and then sends it. Then routing, it selects the best path, selects the best route to the destination. We have the encapsulation, meaning that in that process of the layer 3 trying to learn the source and then the destination, it's doing the de-encapsulation and wrapping. Encapsulation, it's wrapping the package, wrapping the data with the compatible information of at each layer, and then to pair it or to get it ready to be sent on the network medium. IP encapsulation, IP encapsulation, it happens at it happens when a segment, because at the transport we expect segment. So when a segment is wrapped with the source and destination IP address, then there we get the IP encapsulation. So IP can be can use either with so this B4 use IPv4 or IPv6. So IP package will be examined by all layer. So the packet it has to be examined by every network, every layer 3 device. Now with like a network device, it can be a router, it can be a layer 3 switch, it can be a firewall. So as long as that device falls at layer 3, it will always examine it will always examine or review the IP package. So the IP addressing does not change. eh. So the IP packet, the IP addressing, it does not change. So the IP addresses that are set on the source and destination, they will not change in the process of sending a packet from source then to the destination. So characteristics, we expect connectionless, best effort, and then media independent. So with connectionless, it just sends. There is no need of fast. The IP, it's not the responsibility of IP as a protocol to establish the connection. So it's just there. It's like you having uh, uh, post office number or the post office mailbox, the mailbox. So yeah, as long as you have the mail box, the mail address, then automatically you'll find there whichever mail that whoever tries to reach you will send you something, will send a mail into your mailbox. But there is no need of like alerting you, hey, please, is your email working? Are you connected on the internet? Are you this? No. Now here I'm actually looking at the IP. So it's not the responsibility of the IP to first establish the connection so that one can send you a mail. No. So it's just there to logically identify a computer on the network. Best effort, media independent. Now, when it comes to media independent, whichever media you're using, automatically it needs the IP address. So be it a fiber optic cable, be it maybe wireless, be it copper cable, you need the IP IP address. So this is the so when you look at this, it's connection. This is IP connectionless, as you can see. So whoever is here, whoever is sending, okay, whoever is sending whoever is sending a letter will not first confirm maybe, are you at home? Or are you doing this? Are you free? No. This person will just write the letter and then drop it in the mailbox, and that is it. The delivery service van, it will come and pick and then deliver it. Whether you're there or not, it will reach there. So when you look at this, it does not establish connection. There is no control information needed to control that message, how it's going to, when to send, how it will be sent. No, the destination will just receive the package when it arrives. So there is no need of first getting ready, establish the connection, how far have you reached or that. So IP-based effort will not guarantee. So the moment the destination wants the message, or once a message reaches the destination, there is no need of guaranteeing the delivery of the package. So we are not saying that the network, because here it's the packet, you are talking about the protocol, which is IP. So it's not the responsibility of IP to acknowledge whatever it has received. So when you look at this, that this it sent 4 packets, and then the ones that reached there are 2. So the third one, it's not going to be acknowledged. Yes, if it is to be acknowledged, it's not the work of the IP. So there are other protocols that are responsible for that, and that is transport. But here on the network, no, it's connectionless, best effort, and then lastly, media independent. When you look at this, that we have this is copper Ethernet, this is copper serial. Here we have optical, this is copper Ethernet, and then wireless. So it is media independent. is media independent. So the network layer will establish the maximum. So with the network layer, it establishes the maximum transmission unit. The network layer receives this from controlled information sent by uh, data link layer. So this one here, it's done at the data link layer, but it's not done by the IP as a protocol. So IPv4 package, IPv4 is our primary communication protocol for the network. So in other words, this is a default. It's a default. So it's rare to find an IP address assigned on a device. But when it comes to this, like an access point, those are, yeah, the access point and some other gadgets, the default IP version, it is always version 4. So the network header has many purposes. One, it ensures the packet is sent in the correct direction. Is it in the correct direction? Once the addresses are stated, then there is a clear destination. It contains information for network layer processing in various fields. So it contains the information for network layer processing. That the information that is within the network layer, it is used in processing that packet. The information in the header is used by all layer 3 devices that handle the packet. So the information stated in the header, it will always be used by all the layer 3 devices along the path to the destination. So here we have the IPv4 packet header fields. They're there. Contains binary, then contains several fields information. Diagram is read from left then to right. So it's from left then to right. So there are those fields. We have version, we have internet header lengths, the lengths of the header. We have differentiated service, the differentiated service, description, blah blah. We have this, then we have total lengths, we have identification flag, fragment of all this. Then mainly time to live protocol, and then header checksum. We have source IP, destination IP. So there's those that are very crucial, very important, mandatory that have to, in case let's say they have issues, then automatically the communication it won't take place. So these are the fields, and then the fields, and then their descriptions. These are descriptions. So version, it tells which version, is it 4 or 6? Differentiated service used for quality service. Quality, it is used for quality service. Field and then other intensive. So this one here, it identifies which one, the priorities, it deals with the priority. When it comes to types of traffic, the packets, we have voice over internet, we have video, we have the normal traffic. So this it will help to categorize and then prioritize which one should go first or be given first priority. So time to live. Time to live, it's a layer 3 hop count. When this field is when it is decremented to a zero, then the router will discard the packet. In other words, this protocol here, it helps to prevent packets from being sent endlessly on the network. Now, the endless, I mean to be sent from router 1, then to 2, 3, 4, and then it comes back to 1. So it's this field that will help. Then we have the protocol. This one here, it identifies the protocol used in the next protocol. Is it ICMP? Is it TCP? Mostly, is it TCP or this? Identify the transport layer used in the upper layer. Then lastly, we have these two. We have source and then destination. Source, destination, these are the IP address of the end devices. Of the end device. And I remember telling you that, I remember quoting this, that there is no any IP that there is a source, and it depends on the context. So if the IP address is the one is sending, then it becomes a source. The one that is receiving, it becomes the destination, vice versa. But there is no any device that for which specifically open it is the source, no way. On the network, it's not there. End devices, they can be defined as the source or destination of information. Then we have the video here, which is sample IPv4. This video will cover this the following. Well, we have IPv4 IPv4 Ethernet packet in Wireshark, and then control information, then the difference. If I get time, I think I will uh, do a practical on this and then illustrate that. IPv6 packet, IPv4, it has three major limitations, the challenges. One, address the depletion. That this one here, IPv4, it's 2 power 32. What do you get? So now, when you look at the demand, the devices that I need of IP address, almost they are the greater of the number is greater than the number of addresses. So the IP addresses are less than the less than the devices that I need of IP addresses. So lack of end-to-end connectivity. Lack of end-to-end connectivity. What does this mean? Now that the IP addresses here are few, remember this total, this of this one here, it constitutes both public and then private. So if you subtract the private, still now the IP address, this time there will be fewer. So the now that the IP addresses are few, we have two types. We have public and then private. So most of our computers, they are assigned with private, and then when there is a need for internet, that is when they contact public IP address. So when they are contacting public IP address, then the private IP address, it has to be converted. So that is what we're saying, that it lacks end-to-end connectivity. End-to-end connectivity. We have to go through a third party, which is NAT, Network Address Translation, so that the IP address, it can be translated to the public IP address. So increase the network complexity, you can imagine, because now if you have the complexity, you will find that you have so many private IP addresses in the routing table, and they have to be converted every time there is a need to access internet, so that it creates the complexity, the complex network. Complex network to the extent that if you are not an expert, not good network analyzer, you will not understand what will actually be taking place. So IPv6 overview. The IPv6, it was developed by Internet Engineering Task Force. It overcomes the limitations in IP address. The IP addresses are enough. Connectivity, there is end-to-end because the IP addresses are enough. You can use public to public without private. Then what else? The complexity. Now that you can decide to use just a single type of address, you don't need to you won't find that those challenges. So the improvements, of course, those are the ones that I've talked about: increased address space, improved packet handling. Now in packet handling, automatically you see the packet header, IPv6 packet header, the header or packet header fields, they are few compared to IPv4. Then it eliminates the need of NAT. There is no need of using that because NAT, because there is enough public IP address to the extent that all machines, they can be assigned IPv6 address, the public ones. So here is the header. It's the header. It has version, it has traffic. This is almost the same as the differentiated service, and then flow control for controlling the sending and receiving, preload lengths, the length of the header, next header. Now the next header, it's the protocol used in the transport. Is it ICMP? Is it what? Is it ICMP? Then is it UDP? Is it TCP? Then hop limit. Hop limit, it's the same as time to leave. It's time to leave. And then we have source and destination. Direction. These are there to direct the packet. Where is it from and where is it heading PC2. So here we have the description, the table, the functions, and then description. The version, is it version 6? So it's for traffic class. It's used for quality of service and equivalent to differentiated service. Flow control informs the device to handle identical flow label. Then preload, there is a 16 field indicates the length of the data portion or the preload, the size of the data that is being sent. Then intrusion, the next header, which is intrusion detection, the next level protocol. Is it ICMP, is it TCP or UDP? Then hop limit. Hop limit, it replaces, as you can see, time to live. So if it is decremented to 0, then automatically the router that receives that, it's going to drop it. Then source destination, I've already talked about that. Here we have IP packets may also contain extension header. Extension header. So the extension headers, uh, extension headers extension header characteristics, they provide optional network layer information, uh, 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 information, and they are optional. They are optional. These extension headers, they are optional. They provide optional network layer information. The network layer, the optional network layer information still can be done in that and are placed between IPv6 header and then the pre. So if it's just optional, then it will be there. And that option, that is in case it arises in the network layer. At the network layer, then it may be used for fragmentation, dividing, for security, mobility, and then even support and so on. So note, unlike IPv4, routers do not fragment IPv6. So the IPv6 is not always fragmented, but IPv4, it is fragmented. The video here, it will cover the following: IPv6 Ethernet packet in Wireshark, then the control information, and then difference between the packets, different packets. So we have this section here for how a host, how it does routing, how a host routes. Yeah. Packets are always created at the source, so it creates, then the destination receives. Yeah. But we don't have a specific source and then destination. That one, it happens in a context, in a direction. So if the sending device, it's the one that that creates a packet, then the other one receives. So the sending one, it the course it has to create. Then the receiver, it will just receive. So each host device creates, or the devices, they do create their own routing table, because from saying that it depends, the source and destination, it depends on the direction. So every device on the network, it has to create its own routing table, because the sending option for PC1, it can't be the same as for PC2. So hosts can be a host can send packets in the following. Itself, we have loopback interface, which is this. I think I can try it out. Let me try to bring out CMD. So it is here that I can ping any IP address that begins with 127 then .0.0.1. So if I press enter, as you can see, I'm getting replies. So this is just a block. You can actually use this range up to 255, then 255, then dot 254, like that. So as you can see, so if you use the first one, the last one, still you'll get the same results. See? And then for IPv6, it is just this. Then the one like that. You see that you're getting replies. Whether you have internet or not, this is going to work, because it helps to check your TCP stack, whether it's functioning properly or not. Then we have local host. Now with local host, the destination is on the same network. destination is on the same network. Now this is our one network here, this. So if you ping, if you're on this PC and you ping this IP address, you will have pinged the localhost. If you're on this PC2 and you ping this one, you will have pinged the localhost. If you're on this machine and you ping this interface, you will have pinged the local host. You're trying to reach localhost. Then we have remote host. Now, remote host, it's the network. For example, let me just do. We have this router one here connected to a PC. Let me give it one. Then we have another router, which is router 2, connected to PC2. So when you look at this link here, it's not directly connected here. So it makes this network, or it qualifies this network to be called a remote network. Is a remote network. And it's the same as what you're saying here, that this is a server, but it's connected to this network through internet. So it's not directly connected to this router. So any network, because now this, if this PC tries to reach this, it's on a remote network. You will call a remote host. This is a remote host. So this network, even this, even when you're on this side, these two devices, the remote devices are trying to reach the server. Forwarding decision. The source device determines whether the destination is local or remote. So the method to determine the method of determination we have, you can use okay, the IP addresses, the IP address, and we have two versions. Source uses its own IP address and then the subnet mask along with the destination. So if the source and then the destination IP address are sharing the same subnet mask, they're on the same network, and now you're going to, they have network portion, the network portion have something in common, like network portion, or the network portion is common, it is uniform onto the source and then the destination, then automatically that it will tell that, for example, if I have 192.168.1.2/24, this one here, it means that the network portion, it's this. And the total IP address that we're looking at, there will be 2554. And then this side, you have 192.168 dot 1 maybe dot 100 dot 100. So still, when you look at this is the network portion, which is the same as this /24. It's the same. Then when it comes to the range of the hosts, it's totaling to 250. So this, it houses this and then this. So this is the same network. In case, let's say here we had like a 2. So it's a network. This is the network portion, but it's not the same as this. See now, it's not the same as this. So you will treat as this as that they are on different networks. Still the same, it applies to IPv6, the IPv6. So local traffic is dumped out the host interface to be handled by an intermediary device. So when you look at this, that if the traffic is meant for local, so it's this switch that is going to decide where to forward it here or forward it here, period, because it's on the same network. So it's not the responsibility of the router now to decide where to send the package back this side, unless if it's from outside. Then on a remote, when it comes to a remote traffic, it is forwarded directly to the default gateway. So if this PC wants to connect to the remote, then the traffic here, the frame, it's going to be sent directly to the switch, and then the switch forwards it to the router. And then the router is going to find which one is the source and then the destination. Do I know, or is the destination known? There is the information about the destination known in the routing table for this router? If yes, then it will select the best. If not, it will dump or drop the package. A router or a layer 3 switch can be default gateway. So we can have a router as a layer 3, can have a switch, multi-layer, what we call layer 3 switch. So these they can also serve as the gateway, because this they can interconnect. Any device that interconnects the network, then it has that capacity to serve as the gateway, gateway device. But we have what you call gateway IP address. Now we're going to look at that. Features of default gateway: it must have an IP address in the same range. This is my router connected to a switch and then maybe to two PCs, PC1, PC2. So this device, they will be assigned IP address, then subnet mask, and then default gateway. So default gateway that you're going to assign, it should be the IP address assigned here. And it will cut across for both these two. All the devices, even this switch inclusive, that if you decided to put the IP address on this switch, the IP address, the default gateway. Now the default gateway should, I can give an example that if this is, for example, 192.168.1.1/24, then this one here, it can be 2/24, and then this it can be maybe 3/24, and then if you want a switch, you can give it maybe 4/24. So as you can see that all the IP addresses are generated from one network address, which is 168.1.0/24. Because here in this, the range it's going to be from actually 0 up to 255. So these all IP addresses are generated from here. So we have to maintain wherever we want on this network, wherever we want to assign the default gateway IP address, we have to use this. So this is the exit, and at the same time it can be the entrance for any traffic that is trying to enter this LAN or exiting. So here the IP address, the default gateway, it will be this IP. It will be this IP address here. And both on this as the gateway, and then on this as the gateway, and then even on this PC as the gateway. Okay, so this is it. That is what I'm from explaining. This is a network. You can relate it with this. As you can see, this we have two machines here. So the gateway, it will be this IP address. So it will be this, then plus 1 as the gateway. But this is a 10, we have 15. So if you want, you can actually even have 20 here. And then if you want this to be remotely managed, to be on another network, and then you, because now if you use this PC to manage this, they're on the same network. But if I have another network here and then a PC, so for this to be able to manage this switch, the switch, it has to be assigned with default gateway. Then on our switch, we have on our Windows, Windows operating system, root print, or net start -R to display PC routing table. So here, if you want the routing table, you can use net start, then -R. So there are 3 sections displayed by these two commands. This and then this. So we have the interface list where there are all potential interfaces and then the MAC addresses. So when you look at this, we have the links, the interfaces, they are here. Interface. Then we have IPv4 routing table, the routing table. because the network destination, that is it. Then we have IPv6 routing, IPv6 routing table. So we should have the IP, not seeing there. This is a table, interface list for all potential interfaces, and then MAC address. Then there, MAC address, still I'm not seeing there, MAC addresses. Yeah. But the three sections are displayed by these two commands, interface list. Of course, we saw the interface, which are these. Then potential interface list, all potential interfaces, and then the MAC addressing. That's the maybe it was abbreviated, and then IPv6. Introduction to routing. Here you have to pay attention. So routers. So here we have it's just a question. Router packets forwarding decision. What happens when when the router receives a frame from host? When the router receives so the direction it's this. So the router is going to receive a frame. Once it receives, and the frame is going to be received on this interface. Once it receives, then it's going to do the de-encapsulation. In the de-encapsulation, it is trying to learn what's the source and destination MAC address. So if the source and destinations are okay, because we said if it is trying to from the host, the router receives the frame from the host. So it has received. So it will just decompose it and then to check what's the source and where is it, the direction, the direction. So at this point, the destination it is 1010, as you can see this. The destination it's 1010. Destination IP address here it is 10, then this one here destination IPv4, still it is 10 in between this. So packet arrives at gigabit Ethernet on this interface on the router. Then router 1 encapsulates the layer 2 Ethernet header and then trailer. Then router 1 it's going to examine destination IP address. Now once the destination IP address are defined or are known, then the direction, the source and destination will be known. And then such as once this destination is known, then the router is going to search the best match in the IPv4 routing table. So the table available on the router 1 is going to be searched and then see whether the destination is known by this router. So the route entry indicates that this packet is to be forwarded to router 2. So our table is this one here. Let's see, because in the destination we have 10.1.1.10. We have 10.1.1, 10.1.1.10. That is the destination IP address. So we have it here that this is the network, it is known. So if it is known, it's connected to which interface? It is connected to which interface? That the interface it's this, and you have to go through router 1. So that is the metric, the number of hops that for you to reach the destination you have to go through router 2. So router 1, once it gets that information, it's going to wrap the frame, or encapsulate the packet into a new Ethernet header. Now the new Ethernet header will be different with the new source MAC address and then destination MAC address, and then router 1 sends it or forwards it to router 2. So router 2 it will do the same until it reaches the destination. So IP router routing table, there are 3 types of routes in the routers routing table. We have directly connected, we have remote, and then default route. The directly connected, there are these ones here. So we're on R1, this is directly connected network, and then this is also directly connected network. Now when it comes to the remote network, it's this network, as you can see, it is not directly connected on this router. It's not directly connected to that router. Still the other same way, if you're on router 2, this one here is the connected network, this it's a connected network, and then even this it's also a connected network. So it has 3 interfaces. But there is this one here. Now this one here, it becomes a remote network. Why? Because this network here is not directly attached to router 2. So in directly connected, these are routes that are automatically added by the router, and provided the interface is active and has addressing. So once it has the addressing, once you have an interface assigned with an IP address and then activated, meaning that it has to be an active interface, then it qualifies to be a direct. We have remote. These are routes the router does not have directly connected. I've explained that. And there are two ways of learning the remote network. We have what we call a manual with static route. So here we have static route, and then even this route, default route. Then we have the dynamic. The dynamic, it's auto. Uh, uh, it's managed. It's managed automatically. What you need to do is just to enable it, and then automatically it is maintained. It is up-to-dated automatically. Yes, admin's intervention may come in, but there are those scenarios where the admin may not intervene, and then the system or the router, so the protocol, it helps in updating the necessary data updates. So with dynamic, by using routing protocols to have the routers share their information with others automatically. But when it comes to default route, it's also one way of the static route. So like I said, we have static, and then we have default static, then route. So here we have the static route. With static route, as you can hear, it is the stated route. It has to be known that this is the route. Like right now, using previous topology, which is this, that a fella want to create a route. Because this is a remote network, so idea we need the route on how to reach. Because this router 1, it doesn't know how to, the path to use to reach this network. But we can create it. And now we're going to use static. To use static, as you can see, it's this network. So it's IP, then root, this network, which is 10.1.1 and then .0. The subnet mask is 255, then 1, 2, 3, then .0. Then the next hop, we need the next hop for us to reach this network, because we've stated it and then it's subnet mask. But now, which direction should we go to, or should the router use to reach that network? So we can either use the exit interface. Now the exit interface, we can put G0/0/1. Or if you don't want to use this, we can use the next hop IP address. So instead of this, we can put the next hop. Now when you look at this is our next hop IP address. The next hop, this is our next hop, this. So what's the next hop IP address? It's this, not the other side, it's this point here. So it is this IP address that you add. Instead of using this, you add this. So this is what you have. So static root characteristics must be configured manually. That this statement, it has to be done manually. So in case, let's say there is an issue with static root, then that is it. That is it. That root, it will not, it won't be still serving its purpose, because something has gone wrong. So it won't use. Yes, the root, it's there, but where the root connects, maybe the network is down. Now, if this network is down, our root is not going to help. It will help when this network comes back. So must be adjusted manually by administrator. For any change here, it's admin to intervene. Then we have, it's good for small network. You can imagine, because you have to do this for every remote network. So if you have very many remote networks, then this one here is not going to be applicable. It can be applicable, yes, but on a stressing factor. Then often used in conjunction with dynamic routing protocol. With static, it can be actually not only static, but with this, okay, both static and default, they can be used in conjunction with the dynamic routing protocol, as we're going to see in other chapters. So we have another topology. Look at this. Router 1 manually configured with static route to reach this, okay, this R1 will require new static route. If this path changes, then automatically we have to create another path to reach the network that we will have added there. Now we have another topology. If the route from R1 to R2, this is R1 to R2, is no longer available, then a new static route via R3 now from this side would need to be configured. So if you have a primary, this is a static route going through this to reach this. Now if it is down, then the route that you created in the first place, it will not help. So the systems admin has to come into play to create this other route that goes through router 3 as the next hop. We have the dynamic routing, dynamic routes, the dynamic routing. So dynamic routes automatically discovers remote network, maintain up-to-date information, automatically it chooses the best path to the destination, that is if there is more than one route. So if there is more than one route, then the router using that dynamic route, it will to negotiate and find the best and the shortest path to reach the destination, and then finds the best path when there is a topology change. In case there is a topology change like here, that this was the primary route, but because there is a change that this link is down, there is no need of the systems administrator to go on board to start creating another route. The routes are there, there were two, this and this, and then the protocol helped or has assisted in selecting the best route. Now the best route is down, meaning that the other route which was not a preferred route, it's going to come into a play as the new best path. So this is a video, will explain information in IPv4 router routing table. And then here we have introduction to IPv4 routing table. Introduction to an IP routing table. So if you want to display the routing table, you just be in privilege mode. This is the privilege mode, and then run the command show IP route. Show IP route. So once you run the show IP route, yes, of course, the mapping table it's going to show up, or a key, and then the routes. So these are known routes to reach all other network. Any network that is not listed here, or in case of there is no suggested direction to reach on that network, then automatically it's not going to work. Maybe what I didn't talk about, the default, what we call the default route. So in the static, you saw here, we created the route as this. Now, meaning that in case I want to create the other static route for this network, I need another entry of this format. If I add another network, then still I will need the third entry of this format, but putting specific networks. Now with static, here it will allow us to execute 3 entries. But when it comes to default, the difference with default, it will be IP, then root, then 0.0.0.0. Here you don't specify like what we did here. So here we were specific with the network. So here I'm not specific. I'm not certain. Um, I'm not sure of the address too. So I will actually, this here it means that I've generalized each and every network. This route it will help me to reach it as long as it is in the same direction. And then the subnet mask, since I've not specified, since I've not specified the network, still I will not specify the subnet mask. And then the next hop or exit interface whereby I used 0/0/1. I hope you are not going to be confused of this, and yet we have this. We have two options. You can use the next hop IP address, which is this. If you don't want to use this, the next hop it's on this. Or I can use exit interface. So the exit interface, it's that interface, this, that is going to be used to exit that router. But if you exit this, the next hop, if you exit this network in this direction, what's the next hop? It's this IP address. That is what you state. If you don't want to use this, it's what you will always state. Okay. So here, after running the show IP route, then we expect the routing entries, the route entries in the routing table, and those routes are actually identified with initials, with the root sources. We have link directly connected to local interface IP address. So every time you see a link, hello, it means that it's the IP address that we assigned here. Now we have on other, this is other one. So I expect to see two L's, this and this, because these are the networks or the interfaces assigned with IP address. Let's go there and see. We have this one here and then this. So this is 10.1. Where is 10.1? It's in this direction. And then we have 209.225, which is this. Okay. Then we have C. The C directly connected network. Because here we said the L, it's for the specific IP address assigned here. But when it comes to C, it clearly identifies this, all the IP addresses on this network here, this, and even this side. So that is what it means, the C. It identifies the entire network, not the complete network, but it identifies a LAN on the interface. Then we have S, it's static root. Static root was manually configured. So here we have S with a asterisk. We have asterisk. So with this S, it indicates the S, it's only for static root. Now, if it's S with asterisk, then it means that it's default. It's default static root. Then we have O, which represent open shortest path first. We have D, it's for EIGRP, Enhanced Interior Gateway Routing Protocol. So this command shows types of routes. So directly connected, they are combined. You have CL, because L, it's driven from C. Then remote network, you can use OSPF, EIGRP, and then even others. Then we have the default route where we have S with with asterisk. Asterisk. So I think that is the end of this session.